Hey guys, what's going on? I totally apologize. I forgot if I didn't set the date, it would actually show that it was going live. And now I realize that there were people here. Professional YouTuber. I meant to do it, but I'm like, well, I didn't set a date yet, so I'm like, or a time, so I'm just like, I forgot that it literally puts it up, so I apologize. Welcome everybody that was here. Yes, yes, Poindexter. Welcome, Bill. Happy Thanksgiving to everybody here. No. It is not technical different. I literally just forgot. Uh, I did consume turkey. There should be, yeah. There's a little, yeah. You can see some dribble of something white. It looks like that. So I won't elaborate. But it was delicious. All right. Oh God. Well, that sounds like my mother's back porch. He throws all the seed on. Okay, the squirrels and the birds. Okay, all right. You have an excessive. There'll be. See, I think I like 1.27 like turkeys out there, and it's like in New England, you would see the occasional small gaggle of turkey. They are a lot more prevalent nowadays, and they get big. First time I ever saw a turkey flap its wings, fly 6 feet into the air, and then hang on a tree branch. I looked at its talons, and I'm like, "That's a raptor." I had a small replica Deinonychus claw when I was a little kid. That's what it's talent. I'm like, okay, that's a raptor. That's a raptor. But yes. All right. All right. Where are we? Oh, thanks for the W boson. I have that in another thing. Basically, you just go from the relationship between the Z boson and the W boson. It's that has a lovely answer. I think it's like hyperbolic sine of one or inverse hyperbolic sine of one or something like that. And it's the ratio, it's right there. To be fair, part of the definition does kind of have sine and stuff. So I'm like, are you just redoing it? But doesn't it? It's something that equates out to, I think, like a natural log of two plus one or something. It's something pretty. So yes. Sorry, point. Totally forgot about this. Okay. I went and made like another video. I'm just like, okay, I should have just scheduled this. All right. So now that we're here, let me turn on my little background anime music. All right, such a noob. It's like I'm getting ready to go on. It's like, well, I didn't give it a time. That's like, yes. It says you're going live soon. When is soon? User error. I apologize. All right, so let's get back into it. We gotta do the standard deviation for our the claimed self interaction thing by which we are attempting to back calculate what would be a more precise value of the Higgs boson. Basically, if we're I'm trying to exploit algebra for all it's worth and our scientific knowledge. Basically, if we have something like the Fermi coupling constant, if we got that to like 8 digits of precision and we have one significant digit of error at the end there, we should be able to leverage about seven significant digits. And seven significant digits is more than five with the Planck mass. Now, the Planck mass gives us a limit. I realize I should probably actually share the thing. So what we're going to do is we will direct everybody to 4 minutes and 30 seconds into this live stream. This is the point where we're going to direct folks if they have a question about what the heck's going on. So we have a series of conjectures here, basically coincidentally, and recent measurements have provided at least enough evidence for me as a crazy person on the internet to look into this further. Basically, I'm using inspiration from Alpha. What am I talking about? Oh, let's make this big. Well, the fine structure constant, that's that 1 over 137-ish thing in physics. It's people lose their minds over. All right. So this is what we currently believe it is. This is uses this little thing here, this alpha symbol. This is definition. Elementary charge squared over 4 pi, the speed of light, the electric constant, and h bar, the elementary unit of action. All right, or the reduced Planck's constant. It ends up being the electromagnetic coupling constant. Okay. The dimensionless number is very important. All right. However, when we look at this expression, if it's a dimensionless number, you might not have any idea what this comes out to be. It's to be fair, I forget the exact dimensions of epsilon naught, the electric constant, but its numerator, elementary charge squared. So it's charge squared. That must mean this whole dang thing is charge squared. What charge squared? Oh, look, the Planck electric charge squared. Cool. So basically, we can computationally reduce this, so to speak, to elementary charge divided by the Planck charge squared. It gives you a dimensionless number, aka the fine structure constant. Cool. So taking that of what we know by literal definition, blah blah blah. Okay, yes, and so by basically we're going into here. This is how Professor Feynman liked to think of the fine structure constant. This is basically he liked to think of it as its amplitude rather than the square term, which is basically just elementary charge divided by the Planck charge gives you this. So yes, when you compare the two definitions, so by definition we have got to agree. It comes out to be one. So, okay. What we do is, all right, we take that intuition that's like, I don't know what the Higgs mass is. I have no idea why it's that. Divide into the Planck mass. Professor Carroll said this like a month or so ago. It's like, all right, cool. Gives you this number. I have no idea what to do with that number. 1.02 times 10 to the negative 17. That doesn't mean a dang thing to me. Okay. And we literally cite Professor Carroll here. So let's actually go to, God, hold on. I need to go up back to my other account. Oh God, which account? So many people. This one. Yeah, I don't feel like listening to ads. Sorry, I was one of those people. Okay, so let me stop sharing this one. Zoop, and we'll share this one here. Where is it? Oh God! Don't recognize the symbols on the YouTubes. Like what Dick Feynman said when they're asking him to look at the plant that hadn't been built yet. It's like I was pretty good at mechanical drawing in school, but didn't know what the symbols and the blueprints meant. And I waited too long to ask. Sorry. We're gonna do the tab. Dr. Carrie Cesarati. Here we go. All right. And share this real
I
quick.
mean, these days, kind of hard to disentangle, honestly. Yeah, so the hierarchy problem is something specific to understanding the mass of the Higgs boson, which is one of the bosons in the standard model. And the Higgs is the weirdest particle in the standard model by far. Um, it is the only particle that has the properties that it has. So, like I said earlier, a lot of particles sit in 3 generations. The Higgs boson does not. The Higgs boson stands as a very weird outsider that you may have heard is responsible for giving particles mass. And if you want to learn all about that, there's a beautiful book by Matt Strassler that you should definitely check out. But the Higgs boson gives particles mass, has different, what we'll call, intrinsic properties. It's called the spin in specific that doesn't match any other particle. And because of that, effectively, we think.
Okay. Here's the thing. I'm not a quantum mechanic. I'm not a particle physicist. That was Professor Wolfram. But my thing is, when you start saying properties and stuff, my mind just immediately branches out in like a whole bunch of like silly putty to all these different topics and ideas. And I'm just like, well, I played Magic the Gathering. I've played some Yu-Gi-Oh! I've looked at Pokemon cards. I'm like, there are these different attributes and these relationships, and depending on what seems to interact with what different things will happen, and we quantify and categorize some of these different things. I'm like, again, might not necessarily know all the words, but if you tell me that there's a specific recipe, these things go together in a particular way, I'm like, I like games. I'm sorry, that's a terrible way to go into something, but that's just kind of how my mind works. Basically, Poindexter, I'll hear words, and then my mind basically just kind of like shoots out in different directions into potential things that are related to it. So the properties of what? Within a game, a particular card, the property. I used to kind of be a bit of a motorhead. I'm like, one of the things you learn being a motorhead is it will give you up to X horsepower. It'll give you X. You don't simply add in the maximum of those things together. It's a system. A system functions in a very particular way, and if you actually talk to professionals that would do this, they're like, "No, you don't need all of these. You just do this," and it depends on what you're looking to do. Anybody knows? Anybody that needs a twin turbo kit for like a '98 Trans Am WS6? I'm just saying, might still work. All right. Uh, okay. 4 pi stridians. I stand corrected. You are correct. Where are we? Dr. Cicerati, continue.
That the Higgs boson should have a mass 10 to the 18 times bigger than it does. And so this is the hierarchy problem. And the hierarchy is just the mass scale that we expect and the mass scale that we see everything else sitting at. And the fact that there's 10 to the 18 differences, I mean, really 10 to the 32 because it's squared and that's the real first principles number. The fact that something can be off by 32 orders of magnitude from our theoretical predictions, where did that come from, right?
Oh, I'm going to claim we may have a reason or at least potential origin of where that came from. Again, this is a crazy, absolutely insane idea, but we'll get to the data analysis at some point, and it's be a little terrifying. Looks right in the ballpark, my friends. Again, I'm highly biased, extremely biased. I just looked at this with a 3-digit thing. Oh, this kind of works, but then I'm like, nah, I need modification factors. There's not enough data to really support this. More data. Let's see. More data. Which way is the data seeming to trend? And we're not there yet. We're not near that. We'll get there at some point. Okay. So long story short is if you take the Higgs mass, you divide into the Planck mass, and you square it. Here's the thing. To be fair, Sean Carroll says it's like um, yeah, if you we have Planck's constant or Planck's reduced constant h bar, it's like if you ask me what it's in some value of joule seconds or something. If you ask me the numerical value, like I don't know because all good physicists said h bar equal to 1, and they get on with their lives. I'm not a good physicist. I did not set h bar equal to 1. I just went to all from alpha. I did this. I'm like, it's actually not 10 to the 32, at least for this evaluation, dividing the Higgs into the Planck mass. Well, 10 to the minus 34. About 34 orders of magnitude. Again, that's a really small number, but being occasionally anal retentive, I apologize for my French, maybe, but I recognize these first 3 digits. Happens to be the first 3 digits and corresponding magnitude, the h bar, the elementary unit of action. Now, that ratio is dimensionless. You got these joule seconds in here again, like Professor Carroll said, can be referred to as angular momentum, action, or elementary viscosity. I think there's a couple more terms, but those sound cool. Dimensions are mass times the length squared, so it's a mass area. Let's divide by a time, so it's a mass area rate, whatever that may or may not mean. Okay. So uh, basically, we're like, what if it was supposed to equal h bar? What if it was? Oh, that gives us something to leverage because that's defined at 10 significant digits. We got seven for the Planck mass. The last two have error in it, so we got a solid five. Um, let's do it. We do it. Gives us the Higgs mass of this, approximately the mass energy of the Higgs boson. Do some. Okay. So literally all we're doing is we're setting, we're assuming that the value of the Higgs boson, the mass of the Higgs boson, should be equivalent to our expression here. The Higgs mass divided by the Planck mass squared should equate out to the magnitude of h bar. So all we literally do is take h bar and we divide it by one in the reference dimensions. So we're dividing by 1 joule second. That is the dimension of action, elementary viscosity, spin, whatever the heck you want to refer to it as. So we are dividing by one. This is literally the most controversial part. I'm gaining higher and higher confidence that it might not be that as crazy as one may suspect. It gives us this value here. So we're solving for kilograms. Let's give them this 10 to the minus 25 number. Okay. Little graph and everything. So it comes out to be approximately 125.376 giga electron volts. Coincidentally, for shameless self promotion, at least in April, CMS had come out with, believe it's still the most up to date recent measurement of the Higgs boson, and it came out to be 125.38. Currently, at least according to that CMS result, um, maybe it's been updated since then, but at least according to the initial result, um, the the deviation occurs in the sixth significant digit that we technically haven't measured yet. That's why I'm writing a computational essay. All right. Wow, did it take 12 minutes for me to get to a point? I apologize. Oh, so apparently Poindexter, if you notice, if you listen to the full broadcast, Dr. Cesarati and I believe Professor Kerr, you'll hear like 10 to the 6 or 16 orders of magnitude, 18 orders of magnitude, 32 orders of magnitude. To be fair, like, okay, 10 to the 16 squared, it basically just doubles the exponent. So you would get to 10 to the 32. It depends on which one you're dividing it into, but I think he was just kind of wrong. And that's the thing. If you're a particle physicist, again, your job isn't to know like this exact magnitude and stuff like that. You set it equal to one, you move on with your lives. It's kind of like if somebody says like the Planck length is like 10 to the minus 33 meters. I know they mean centimeters, but it's like you say that people generally know what you mean. It's approximately this. Okay. Now I just might happen to be maybe a wee bit spectrumy and occasionally pretty good at remembering, or I just put it into Wolfram Alpha and you can see the calculation. Now, again, that's just a really small number, and there's no reason to know that. I've literally typed in either the digits of H bar or I'm pretty good at remembering the first couple of digits in exponential powers to things if I see them enough times. Just pattern matching and just doing gaming enough. You're like, oh, I've seen this before. I've seen this before. That reminds me of this. Let me go double check. Oh, and then I just take what Thad taught me. It's like, that was a pretty cool thing. What if I assumed it's true? Also, if you could just plug this in, I'm pretty sure starting for somewhere in the weak force or the expression for the Higgs mechanism stuff, there's an H bar in there. So if it's literally tuned to that, I feel like we can make things easier. I feel like if we can learn something new again, maybe it's probably nothing. Probably nothing. Most likely scenario. At least worth me about this and at least going through the process. Yeah, exactly. I don't expect somebody to remember all nine digits to the speed of light. It's occasionally you run into somebody that's maybe gone through it a lot. Like I remember the first time, it's like when I see Thad recite the 10 digits to the speed of light off the top of his head, and Thad like corrects me, like, we only have it measured to nine. Accurate. It's some people have gone through. We'll see. We'll see. Oh, thank you. No, that means a lot, Dexter. It's to be fair, I have no idea. I'm just looking for computation reducibility and simplicity. The only reason I knew that little thing about the fine structure concept, I was just playing around Wolfram Alpha. Like, what is this? What is the square root of this? Oh, look, it's a blank charge. To be fair, I think I recognize the squared version because Thad has it in something like that. So I kind of remember the tail end and the power. But interesting. Charge squared does not have a definition unless it's related to something else. Yes, as I wag my finger in the air. Yes. Welcome, Mike. Happy Thanksgiving, my friend. Oh, God, we haven't even gotten there. Sorry, I've been bloviating the whole time. Okay, so we finally explained ourselves and it only took 20 minutes. So we're in here. We're making wild assumptions that the Higgs self interaction, if we plug in that number and we do the whole computation for this is basically it's the Higgs vacuum expectation value. About it's about the mass energy of two Higgs bosons, a little bit more. Long story short, when you put in these six digits, you get this thing. Yeah, you get enough information to put output that. And to be fair, when we output even a few more digits, okay. Long story, we get these digits. I'm gonna have to go up there and correct some of that. Long story short, is the best fit for that happened to be this. This also happens to be probably one of the simplest versions. And I ignored it because I completely forgot the significance of this G sub GE. Gelfand's constant. So 3 divided by Gelfand's constant, which is literally defined as E, the base of natural logarithms raised to pi, the constant of curvature. It's also the sum of all even dimensional sphere volumes. It's being divided into three. Again, I have no idea if that is true. We're using this and trying to backtrack a Higgs thing. It's my level of confidence is like, all right, if the fine structure constant can be defined as basically elementary charge over the Planck charge squared. So elementary thing divided by a Planck thing squared leads to an important number. Okay. So what if we just took, I don't know, an elementary thing divided by a Planck thing squared it, and when we assumed it was supposed to be an important number. Now again, one is a dimensionless thing, but occasionally there are calculations where we'll literally spit out like the string of digits for the fine structure constant in dimensional quantity. I only know this because I've gone down so many dang Wolfram holes. Also, if you look at what is it, Planck impedance, the basically number of ohms, so to speak, um, basically just about the impedance of air itself, and the string of digits it goes like 229.972, I believe, because it's literally the same digits as the speed of light, just in a different dimension. Um, Noticing that, I'm like, all right, well, if this thingy up here, so if we have elementary charge over the Planck charge squared, and that's the same as this whole jazz by the definition of the fine structure constant, and it's equal to one. If I take an elementary thing of charge and divide it by the boundary of charge and square it, we get an important number. What happens if I take an elementary thing of mass that we assume suffuses all of our realm, so to speak, divide it by the boundary of mass itself, we square it, and we get an important number. To be fair, h bar does actually have a dimension of mass in it. It's literally got the Planck mass in its first term because mass, area, rate. Basically, it's you're gonna if you do Planck units, you're gonna get h bar. At least you're supposed to for X number of digits. Playing seems to seems to be an interesting thing. So, all right. Uh, all right. Okay, so we were looking at different relationships where. Oh, look, the Planck mass again. We need to do this for. We need the Fermi coupling. There we go. Oh, up or down. Uh, feel like maybe you got yes. Okay. All right. Yes. Yeah, there's a lot of assumptions between there and here. We have this. We check plus and minus. Let's go three standard deviations. Oh no, we did one before. One standard deviation. H plus slash minus plus one deviation. Okay, we might go further depending on how much we'll throw at a whack, but it's pretty far out there. So wait a second, hold on. One, two, three, four, five, six, seven. We got seven standard deviation. We got seven digits there. So if five digits, okay. Let me hold on. Let me. One, two, three, four, five, six, seven, eight. We went three standard deviation. Okay, if we want four standard deviations, then it would be one, two, three, four, five. Okay, we still got six. It's even a smaller magnitude. Okay. Hmm. I'm just thinking if that was a 2, 4. I'm sorry. I was just randomly pattern matching though. That was. All right. Sorry. So we're going to assume we have this measured really well. So we needed our other expressions. Uh, all right. So think I'm just literally gonna. Will it let me get away? Will it let me get? Oh, because all we're literally just doing is swap. Oh, why do I think this is gonna break epic? It understands GeV. 873787. 3787. So let's go up. So that would make this 9 and 3. All right. And 3 in the last two digits. 3 times. Okay. Will it work? Enable dynamics. I'm gonna do it. Nope, it did not understand the types. I'll try. We'll do it the old-fashioned way. Oh, all right. Oh no. We're putting in more precise. Oh no. We're solving for x. That's what we're doing. All right. Solving for x. How did we do it? Exactly? Oh, we're setting it equal to that. EV. That's what we're. Okay. I know. XGEV squared divided by. This took so long yesterday. Square root 2. This is why it confused me. Now we have 1.1637. 1.166363737. And that's going to be 9.3 times 10 raised to the -5 GeV and -2. Okay, this is where we do the negative. Negative. We got to inverse the thingy. Now, okay, so where this one? That equal to 3 over Gil funds. Save as. Exactly 33. Because after all that, I know myself. Been going over for half an hour just rambling on. All right. Now you're actually going to do something. Of course, it will most likely crash. Loading and save. Go. Hmm. All right. There we go. Now, all right, we change it. All right, so now we hit enter. Give me my results. No, it's doing the thing. Need a. It's doing the thing at the. Okay. Giga elect volts. Giga electron volts. It may or may not be breaking apart the G, E, and V into variables. I mean, look at what I'm putting in. This is not the most common evaluation, I would assume. And when I you're gonna use Gelfand's constant with like GeV or something. Maybe a factor. Where are we? Okay, so give us that. We don't need this. You, you, you. This is all plus one. One standard deviation. Going and put an actual little sigma there. It's my own note keeping right now. Okay, so we close. Now we need to go back. Fermi constant 87. Now we're going to do minus one. So that'll be 8-1. One, go, put, very minor difference. A lot of significant digits. I'll put that. Up, up, go. So, one, minus one. Radiation. Safe. Disorder. Boom. Right. That. Okay, we can use that for a future computation. I'll throw you below our here because now we're gonna reevaluate here. We need doing this for the Higgs mass. I'm so bad. I'm like, compute for me. Let's do this. Or seven. Not gonna reckon. Almost got it. Alphonse. And now? Nope, I should think I'd learn by now. 8.2 or so. I know I can do that. Continue on. I'll learn additional tricks later. 8.247547 times 10 raised to the negative 6 squared equals 3 over kilofons. Oh, it's giving us literally like the exact same thing. So we're literally the same thing as before because it should have a little deviation after. You up, roll you up. Okay, I got that. Oh, that's fine. We compute for these guys. One is 2, 4, 7, 5, 1, 5, 3, 9. 3, 9 times 10. Okay, all the same. Dude. Oh, looky. The literally showing gets like, seems to be right around there. All right. See. Very, yeah, you can see it's rounding there. So I'm assuming it's not just going to do the exact same thing. It's actually going to compute for as many digits as we output. It could be totally wrong. It may just be making all these things. You up, you up. Okay. These guys here. You guys. Uh, you over here. If keeping. Okay, so we. Oh, I'm gonna have to set. This is getting annoying. Oh, that's there's something unwise here. It's 34. Let's say that's a good number. Then I just realized be wary, be wary of Rule 34, my friend. Don't go gold Rule 34. Eve, la, that one. There we go. Hey, Mr. Grimm, what's going on? Yes, I know, my dude. I know. It's a good thing I have Wolfram Alpha and become a lot more. Apologize for the terminology. Less they retentive about saving stuff and things. All right, now I'm going to attempt to um, open. I'm just going to separate these things because it bothers me. But delete. Do I understand at least enough deleting? There we go. Yeah, that's more pretty. So we're being honest. We're showing our positive and negative answers. So, boom, you go there, and this should big money, no whammies. At least no whammies. Okay. So we managed to separate those guys. Once you've made any type of useful progress, all I know is when the notebook crashes or any program, it's things seem to be imperfect, and it can it can be quite, especially when you barely knew what you were doing, and it's like it somehow managed to work. It seems to become easier over time. Okay, so that's almost like human beings have the ability to learn different stuff. Well, look at me. I'm just a monkey with a magic typewriter. Ah, uh, Grim, we played those games. Oh, God. I totally got one shot. Seems about right. All right. I think we did. All right. Well, oh, we're gonna have to do our little analysis thingy. So, okay. Gonna hit enter. Let's see. Actually do something? Oh, like that. No. Okay, the numbers look a little different. Let's see. 3748. 3747. Okay. Hmm. 47. Yeah, the digits are different. Very little bit. God. 3, 4, 5. Where did I put the bar before? 2, 3, 4, 5. No, excuse me. 1, 2, 3, 4, 5, 6, 7. I did it. It's the difference between a 7 and an 8, isn't it? Not even going to be enough data. 7, 4. First one is plus 4, 7, 4, 1. 7. Yeah, I think it might just be making up digits from there because I'm like, if this is straight in the center, and the first one is +1 deviation to. Oh, I didn't even add in Planck masses. No, no, because we're calculating the Higgs boson, or we're claiming. That's what we're attempting to calculate. Okay, so we did that for there. 3747. 7, 4, 7, 4. Oh, it went up. Okay, 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 okay. Because we're dividing it. Okay, so when the bottom thing, okay, when your denominator goes up, you're going to get a lower answer. Okay, 4, 7, about the same. 1, 9, 4. Right, so that means this. Do the same thing. Then we have to do the same thing. Bar there, bar there. Okay, so we're literally same as before. 3747. And, oh, we're trying to calculate. Oh, I'm trying to calculate the Planck mass. We're doing the same thing. Again, I'm just gathering the data. Either I learn and or I ask to help me to code because well, that's why I'm going to cite chat. And anything else that helps me. I did it for the notebook assistant too. I think was pretty useful. This is plus +1. You guys over here. All right. Turns the same. Before. Fix that. And then the other one. Or 8. I really probably should. But I mean, it's you only have so much data. Uh, no, what a fascinating thing. Definitely some intense wrestling with some stuff or things. Correct. Go to hit enter. Dun, dun, dun. It gives us the same thing. I mean, maybe actually, to be fair, that's a good thing. It's clustering around, and I mean, it's giving us what one, two, three, four, five, six, six significant digits. Seems to be within the error bars, and that's the basically the big thing we're checking. As long as it's at least actually one, seems to be in there, unless there's some minor deviation. Basically, if you're within 1 sigma, people usually don't question. Or 5 sigma, 5.5, 7, 10, 20, people probably have some questions. They can refute with the experiment, and that's what we're actually measuring, or we believe we're measuring. Dude. And I'll put this, dude. Really be surprising. Um, Elite. Elite. Well, stuff. I think this is going to be a bit of a shorter one here because I'm slowly, I think, recovering from a food coma, and I should probably go and run and actually, I don't know, trying to get back into the old groove of things. So we need to Put up just the pasta. The value, I think, was the last root. Yes, the fifth solution. Keep solution five. Don't get anything. I'm assuming the Planck mass is positive. I don't know. Maybe there could be another sign. Maybe there's an. I also want to make a little meter. There we go. Doing us that. Be the same. Root. Many roots. Here's what I'm gonna do. I'm gonna save this again. Save. Save before we do anything else crazy. So, since I have these, here's what we're gonna do. I did some calculations. I'm gonna do it one last save. Save this. 5, 8, cloud. Yes, I am that guy. Not, not a cloud walker or a skywalker. I'm just totally lost things before. And you know, here is what we're gonna. And, oh God, why does it keep on defaulting to that? 5. Flesh. All right. Got clipboard. All right. The whole reason I'm doing that is so I can just hit enter for this. I'm like, oh, the additional. Okay. 105. That's really dang close to 1. Still within the error bar. So 4105. 412. Okay. So there is deviation as we would expect. A little bit more safely in the error bars, but error bars nonetheless and tending towards the lower statistical value. Now, again, I'm totally biased. I would love for this to be true, but ultimately, here's the thing. You're going to have to go by experiment and continue to probe as best we can, trying to account for as many of the different things going on as possible with the stuff we have categorized in a coherent fashion. Yes, I start to do that thing when I start doing the little mantra that I learned from Duvid and everything. But yeah. Long story short is if there's some there, then we would expect the Planck mass to be on the lower side of this error. And rather than just 3, 4, going up to 5, 8, we would expect it to be closer around a 4, 1 thing. Okay. Whatever that might be. As we get better precision, we should be able to falsify that. Be like, means no, you're totally wrong. That's not the avenue to go. It's fine. Move on with life. But we'll see what happens. We should be able to now. What we don't need to save because I just hit the things and okay. So with that, have a happy Thanksgiving, everybody. And let's open for a better tomorrow. Always try to be hopeful, but If we could make a difference, wouldn't that just beat all? Peace out, everybody.